Hello students, welcome to the second module of this course in trigonometry. In this module, we will study the graphs of trigonometric functions. Our study is going to be divided in 5 sections. In the first section, we will have a relook at the unit circle definitions of the trigonometric functions and some general concepts in graphing. And then we will start with the graphs of sine and cosine functions using the unit circle definitions and the values around the unit circle. Then in the second section, we will generalize the sine function. Sine means sine and cosine. And that generalization will involve what we call the transformations of functions, the concepts of reflection, rotation, stretching, shifting, that you might remember from your college algebra or your pre-calculus class. And in the next two sections, we will study the graphs of the other remaining trigonometric functions. We will not go into as much depth as we do for the sine and cosine functions, but we will look at their general shapes, their domain and ranges, and the values at which those functions are not defined and how does that appear in the graph and those kind of concepts. Okay, and finally we will look at combining these trigonometric functions with algebraic functions. How does a polynomial and a trigonometric function, when you compose them, how do their graphs look, what are their properties, how can we identify them, and so on. Okay, and for all of these topics, wherever possible, we will be looking at their applications as well. Okay, with that general introduction to the chapter, let me now get into the first module, first subsection, which is the unit circle and graphs of sine and cosine function. Okay, now in this video, in this section, we are going to do three things basically. We will first review the basic concepts of graphing and have a relook at the unit circle definitions of the trigonometric functions. Then we will start with graphing of sine and cosine functions. And in the process, we will of course talk about some general properties of these trigonometric functions called periodicity and phase shift and amplitude and things like that. We will get an introduction to those ideas. And then we will move to the concept of transformation, stretching the graph and moving the graph around. And with that, we will wind up this section. So we will be ready to study the general sine wave in the next unit. Okay. And now let us get started step by step. Okay. Recall. Okay. This is all review. If you have a unit circle like this here, whose radius is 1 unit, and suppose you are taking this angle alpha here, and you take any point xy on the circle. Okay, now the definitions are cos alpha is adjacent over hypotenuse, which turns out to become the x coordinate in this case, and sec alpha would be its reciprocal, so that is 1 over x. Sin alpha is the opposite over hypotenuse. This was cos alpha, okay, and sin alpha is here. Opposite over hypotenuse, and opposite is y coordinate and hypotenuse is 1, so y coordinate on the unit circle is the value of sin alpha. Cosec alpha is the reciprocal of that, 1 over y. Tan alpha is the ratio of opposite over adjacent, right? So that will become y coordinate over x coordinate, and cot alpha, it's reciprocal, x coordinate over y coordinate. Okay. And when we write these reciprocal functions, we make it a point to mention what cannot be zero. Whatever is in the denominator should not be zero. Okay. Um, it is defined for those values or those points where that denominator um, quantity is not zero. When it is zero, those values will not be in the domain of that function, and the function will be going to either infinity or minus infinity at those points, right? Okay, let us review some basic concepts in trigonometry using the unit circle and also some general ideas in graphing. This will help us, get ready to start graphing the trigonometric functions. First, find the exact value of these trigonometric functions at those points using the unit circle. Okay, we have done this in the previous lesson, that is why I say it is a review. Cos 0, right? The definition of cosine is x coordinate. So if I'm evaluating cos 0, I'm looking at the x coordinate on the unit circle corresponding to 0 radians, and that's on the x-axis, and its value is 1. Okay. Similarly, cot pi over 6 would be x coordinate over y coordinate corresponding to the point on the unit circle with angle pi over 6, and that again from your trig butterfly diagram from the previous lessons, activity, you should have it handy, or even better, you should have it memorized. The coordinates are root 3 over 2 and 1 over 2 when your angle is pi over 6. I will not write it there, okay, it will be cluttered. Let me maybe just indicate it here. Okay, this corresponds to pi over 6. Okay, these values, root 3 over 2, 1 over 2. So if you apply that here, cot pi over 6 will be x over y. So that is root 3 over 2 over 1 over 2, and that becomes equal to root 3. Okay, and cosec pi over 3, you can think of it as reciprocal of sine pi over 3. No, although you can just think of it as reciprocal of y, 1 over y, but it's more frequently we remember it as reciprocal of the sine function. Okay, now sine pi over 3, sine itself is y coordinate, and y coordinate where? When the angle is pi over 3, that is 60 degree, and at that point the angle is root 3 over 2. The y coordinate is root 3 over 2 corresponding to 60 degree on the unit circle. Okay, so this, if you simplify, will become 2 root 3 over 3. Work it out. Okay, next, that was evaluating trigonometric functions using the unit circle and the definitions that we just wrote. Next question is about how do the points change their coordinates when you move them in a coordinate system where on the x-axis you have angles like 0, pi over 2, pi, 3 pi over 2, and so on. On the x coordinate you have your scale is in angles, okay, in multiples of pi or in some fractions of pi, while on the y-axis you have like integers 1, 2, 3, which will be the values of the trigonometric functions. So in such a system, coordinate system with that kind of leveling, we will try to see how what happens when the points move around. Okay, what will be the new coordinates? So here you are asked to move this point 2 pi 0 through this transformation. Okay, I'll just call it transformation T. What is the transformation? Moving it pi over 4 units to the right. What will be the new coordinates? And the answer to that is, if you move it to the right, your x coordinate is increasing by pi over 4, right? And the y coordinate is not changed. Okay, and simplify that, you will get 9 pi over 4, 0. Next, take the point pi over 2 minus 1, which is where? In the fourth quadrant, right? And you are moving it 3 pi over 3 units to the left. So if you move a point to the left, your new point, okay, new point is going to be that pi over 2 minus pi over 3, because you are moving it to the left, right? So again, no change in the y coordinate. The y coordinate will change if you move the point up or down. Okay, here you are moving the point to the left or right. That changes the x coordinate. And if you move to the left, you are subtracting, your new x coordinate is lesser than the previous one. So subtract pi over 3. And that, if you simplify again, you'll get pi over 6. Just do it. Okay, that will be the new point. Next, find the coordinate of the point negative 3 pi over 2 comma 1 after it is moved pi over 6 units to the right and 2 units upward. So basically, you see we are doing bunch of similar simple problems, but we just want you to feel comfortable, okay, doing, this transformations, especially not x and y both are not integers. Okay, x is in pi because it represents angle, and we are trying to get used to that, and y will be the values of the trigonometric functions, which is in integers. Okay, and so let's say you have a point 3 pi negative 3 pi over 2 comma 1, and you are moving it pi over 6 units to the right. So new coordinates, okay, let me write it that way, will be negative 3 pi over 2 plus pi over 6, right? You moved it to the right, and then you moved it 2 units upwards, so that y coordinate you'll add 2 to it, plus 2. Okay, you move it up, and now you simplify it, your answer will be minus 9 pi over 6 plus 1 minus 4 pi over 3. You can simplify it and check. Okay, and 8 pi over 6, that's cool. Yeah, minus 4 pi over 3, and 1 plus 2 is 3. Okay, again, maybe this is a little complicated calculation, so I will just show you the calculation separately. What I did was I converted that 3 pi over 2 to having the same denominator as the other expression, because I need common denominator, right? I multiplied by 3 and 3 up and down. So 3 pi over 2 became 9 pi over 6 multiplied by 3 and 3, numerator and denominator. Okay. And when you do that, in the next step, you will take that negative 9 pi and add pi to it. And that gives you negative 8 pi over 6. And then you cancel 8 and 6 and you get 4 pi over 3. Okay, divide by 2. All right. here's another thing, in coordinates. Sometimes we have to find the midpoints of a line segment. So determine the point that lies midway between pi over 6, 1 and pi over 2, 1. So you can imagine this is a horizontal line segment because it has the same y value, 1. Okay, so the y coordinate will remain the same for the midpoint as well. For the x coordinate, you will do the calculation pi over 6 plus pi over 2 divided by 2, right? That is the formula for midpoint, x1 plus x2 divided by 2. y1 plus y2 divided by 2 will still be 1 because it's 1 plus 1 divided by 2, or it is just a horizontal line anyways. So I know the y coordinate will be 1. Okay. Now take 6 common denominator in the numerator. You can multiply up and down by 3 and 3. So you get 4 pi over 6 up there. Okay. And then you're dividing that by 2, 1. And if you try to simplify that now, that 2 will cancel with 4 pi. Okay, it will be 2 pi over 6, which you can again cancel and you get pi over 3. Okay. In these kind of cases, these two multiply. Remember that it will become 6 times 2, 12 in the denominator. So 4 over 12 is 1 over 3 after you cancel. Okay. So we reviewed some basics there. We are ready to start with graphing the sine function. Okay. Let us see if we can go back to our unit circle definition of the sine function and sketch its graph. Very interestingly, just by looking at what we call the quadrantal angles. Okay, for now, using only quadrantal angles. So it will give you a very, very rough estimate of the sine graph, but sufficiently enough as it turns out. Okay. Later we will talk about using more angles, and maybe for some other ratios we might need more than just the quadrantal angles. Let us do this first. Okay. So we are looking at the values at 0 degree where the coordinate is 1, 0. I'm going to go around and write the coordinates. At pi over 2 where the coordinate is 0, 1. At pi, let me also write the angle next to. Okay. So this 1, 0 corresponds to 0 or 2 pi in terms of the angle theta. Okay. Or angle x here. On the x coordinate you have the angle. And this corresponds to angle pi over 2. Then on the left side you have negative 1, 0, which corresponds to angle pi. And below on the negative y-axis you have 0, negative 1, and it corresponds to angle 3 pi over 2. Okay. Let us fill this table now. And we will recall that the definition of sine function is any sine. Okay, so irrespective of the angle, sine is y coordinate. That's the definition we are going to use. So at 0 degree, okay, maybe I can highlight a couple of them. At 0 degree, the y coordinate is 0. So sine of 0 is 0. And when you go to 90 degree, the y coordinate is 1. So sine of pi over 2 is 1. Similarly, at pi, it will be again be 0. At 3 pi over 2, it will be negative 1. and at 2 pi be back to 0. Okay, that is the um, those are the values of the sine function at quadrantal angles. If I try to plot them, will I get some idea? Okay, let us try. So 0 radians is here. Let's say this is pi over 2 radians. This is pi. That's 3 pi over 2 radians. And finally 2 pi radians. Okay, each unit is pi over 2, 90 degrees. So the first point on the graph is 0 at 0 radians. At pi over 2, it's 1. Sine pi over 2 is 1. And at pi, again, sine of pi is 0. At 3 pi over 2, you have negative 1. And finally, at 2 pi, which is equivalent to 0, sine is the y coordinate, so it will be 0. Okay, so I see these dots. And then I'm thinking, this obviously is not a straight line, so I can join triangle, and like straight lines like that and make it an angle of the triangle. It cannot be like that, right? This is a sine function, not a polynomial, not a straight line. So what we do is freehand smooth. You want to catch the word, you write that here. Okay. Sketch a freehand graph. Okay. And I've said freehand there, but I will add, a smooth graph. I will not put it in writing, but I'll just say it. So smooth means you are not suddenly making a V-shaped turn, no? You are making more like a U-shaped, smoothly. Okay, if you do that, you get this graph. Okay, and that, if you see, after that it repeats. Or if you go to the left, you will see that it actually repeats. Okay, so it will be something like then it will be in the fourth quadrant. So yes, it will be like this if you continue on the left. Okay. All right. So maybe I need to put down here carefully and like that. When you look at the graph of this function here, you noticed something very interesting, right? If I look at the values from, by the way, this is at negative 2 pi. I just glossed over that. You can actually verify that. That's how you will get the values and verify. We did check the values on the right side. Okay. And you notice that whatever graph you would have got from negative 2 pi to 0, you are getting the same graph again from 0 to 2 pi. So this feature that you see in the graph is called periodicity. The values of the function repeat. Sine of 0 is the same as sine of 2 pi. And if you go to if you move another 2 pi units, you'll get the same value again. And not just 0, any other angle. If you are at 90 degree and add 2 pi, you'll get the same value, 1. Or if you are at any random angle, like let's say 45 degree, which is pi over 4. And if you add 2 pi to it, you'll get the same value that it had at pi over 4, right? Because of the unit circle, the circular definition here. 2 pi is one complete circle, right? And not only that, the values repeat in 2 pi, because you might wonder sometimes it repeats even before that. Like for example here, I'll draw it in green points. Those two values are the same, right? But is that the period then? So the thing is, on the left side it is increasing and on the right side it is decreasing. So values being equal is not enough. Okay, everything else also should be in a similar situation, and that similar situation will occur after 2 pi. Like, if after 2 pi, if we are somewhere here, you will have that similar height, and not only similar height, the function also is similarly increasing. So the period is that length. Okay, where it when it repeats. That idea we will fill in the blanks now here. Periodic functions. The sine graph, as you can see, is a periodic function. Okay, a function is said to be periodic if its values repeat at a fixed interval on the x-axis. Okay, this is important. The values repeat at a fixed interval. So it cannot be random or it cannot change. After that length of interval, it should, the same value should occur again and again and again. Correct. Okay, both on the left and right. The length of smallest such interval is called its period. Now, in this definition, this word smallest is important. Okay, it's not just casually thrown in. That's an important word, because if the values of sine x repeat after 2 pi, they will also repeat after 4 pi, right? If you keep adding 4 pi, the values will repeat. But they also repeat after 2 pi, and 2 pi is the smallest value when they repeat. That smallest value is the period. Okay, that's what we are saying here. Next, the graph of a periodic function over one period of the function is called a. Now, if you just look at the graph from 0 to 2 pi, okay, I will portion it off here. This portion of the graph, okay, between 0 and 2 pi or one period, doesn't have to be only between 0 and 2 pi. It could be between negative 2 pi and 0, or it could be from, I'll show you one more. Okay, it could be between minus pi and plus pi, like that. And you can see that it always looks the same. Okay, so if you any portion of the graph with that length of one period is called a cycle. We call it one cycle of the graph. Okay, and to fill in the blanks here, we already discussed the graph. The period of sine x is 2 pi, as its graph makes it clear. The graph of sine x over the interval 0 to 2 pi. Now, we said that you get a cycle if you take any interval of length 2 pi in the graph of the sine function. The particular one, the red one that I have encircled here with red boundary, that interval is 0 to 2 pi, right? That particular period is its fundamental period per cycle. Okay, and the reason for that we will see later, because when we want to know the solutions of an equation, we generally be interested in the value that lie in the fundamental period or in the fundamental cycle. Okay, all right. And now we'll look at some key points, literally points. Okay, not key point, actual points on the graph of one cycle of a sine function. Let us look at it. Okay, and we could go back, but let's me actually quickly sketch it over here again, so the reference will be easy. Okay, so the graph of sine x, we saw the fundamental period was this, right? And the markers are 0 here, pi over 2 here, pi, that's 3 pi over 2, and over here 2 pi. Okay, what are 5 key points? Uh, 2 points are this, the highest and the lowest points or extreme points. Okay, two extreme points which refer to max and min. Okay, and then you notice another very interesting point here. Okay, it is interesting not just because it is zero, that is also one thing, but more important than that, or maybe equally important, is before that the graph is facing down, what is called concavity, right? Hope you remember that concept from again college algebra or your pre-calculus. This part of the graph is concave down, the next part is concave up. Okay, and that point at pi is in between, right? Exactly the boundary point where the concave down changes to concave up. That point is one inflection point. The name of such a point is an inflection. Okay, so two max and min points, one inflection point, and what two more can we talk about? Two more would be this, the other two zeros. Okay, you have zero here and two. Okay, uh, two more. Okay, um, if you include one, the inflection point, if you include pi or the value pi also can be included, and the two more points, which are quote unquote mean positions. Okay, in the graph, if you see at 0, pi, and 2 pi, the value of the function is in the average, in the mean. That mean position is exactly halfway between the two extremes. There is one highest point, there is one lowest point, and there's the midpoint, right? The x-axis. And there are 3 points on the graph which have that mean or the average value. One of them is also an inflection point. The two others are um, average or the mean points, mean position points. Okay, so these are like important points in the graph. We are studying the graph. Okay, all different features of it. Let us now repeat the entire analysis for cos x. And this time I will move a little bit faster because you know the drill. All the same things we are going to repeat now. What we did for sin x, we will do for cos x. Okay, let me quickly write the units 1 0 0 1. I mean write the coordinates -1 0 0 -1, and cosine x is x coordinate in the unit circle. Okay, now don't confuse that x coordinate with this x, that is different. Okay, this is angle x, not the x coordinate. Okay, so we use x for both of them here. You have to be very clear which one we are talking about. When I say cos x, that x is the angle x. Okay, what you normally, otherwise we used alpha earlier, right? We used to have alpha or theta for that angle. That is x here. Okay, when I generally write, because trigonometric function is a function of the angle, so as a variable we use x here, but you need to understand. And when I said x coordinate, I'm talking about the x and the y coordinates of that point. Okay. Now let us graph the function. Because cosine is x coordinate, at 0 its value is 1, at pi over 2 its value is 0, at pi its value is -1, at 3 pi over 2 again 0, and 2 pi back to 1. And now you can take those values and sketch a graph. At 0 the value is 1, at pi over 2 the value is 0, at pi the value is -1. Okay, at 3 pi over 2 the value is 0 again, and at 2 pi value is 1 again. Okay, so these are the values of cosine at all those quadrantal angles. What kind of graph could you draw which connects all these points in a smooth way? Okay, now you could actually take a straight line kind of thing almost. Okay, but it looks like that because of the scale. Actually, pi over 2 and 1 don't have the same length. Okay, so remember pi is 3.14, so pi over 2 is more like 1.57. So maybe I should have, if I wanted to make it more realistic, I would have taken a graph where the unit on the x-axis is a little longer, like 1.57, whereas the unit on y-axis is 1 unit. Okay, so but you understand it and keep that in mind when you are looking at the graph here. Okay, so I am thinking of a smooth graph which touches all these points, and as you can imagine, it's going to be smooth decreasing here, and then between here and here it will change its shape, then again smoothly rising there. That would be one fundamental period of the cosine graph. Okay, one cycle of the graph, and from 0 to 2 pi is fundamental. Okay, the period of cos x is 2 pi. Again, you can see that a fundamental of sine cos x is over the interval 0 to 2 pi. Closed interval is typically we write. Okay, and what are the key points? Here's the graph. The key points on the graph are your starting point and your ending point, which are also max points, maximum points. Okay, and there are two inflection points. Now here it was concave down, and in between it is concave up and again concave down. So the concavity changes in 2 points. So there are two inflection points, and there is only one minimum. Okay, you should check all the coordinates here. Okay, next we look at the transformations of some graphs of sine and cosine. We will begin with an exercise. Look at the graph and determine the coordinates of P, Q, R, and S. Okay, and then we will see what that means. I will write the coordinates over here. Take P. Okay, the point is here, and in our graph here is x-axis, here is y-axis. Okay, and if you see the point, the reference is here. That point is 2 pi comma 1. So it looks like P is on y-axis at the same height, so its coordinates are 0, 1. Okay. Then if you look at Q, it corresponds to height 3. What is the x coordinate? For that, let us look at the markings on the x-axis. That's 2 pi at the end there. So we must be having a pi here. And that means this one must be pi over 2, and here we should be having 3 pi over. Okay. So Q seems to correspond to pi over 2 on the horizontal axis and 3 on the vertical axis. And R is now at pi on x-axis and 1 on the y-axis. Okay, the level 1. And the point S is at 3 pi over 2 on x-axis and level -1 on y-axis. Okay. With this, and after identifying the coordinates of these points, does that give us an idea about how this graph was obtained, starting with either a sin x or cos x? Which one could you do a transformation on, right? We are trying to explore the transformations. So how could you start with sin x, and what transformations would you do to get this graph? And will that help us write its equation? Now, this is an advanced exercise, as I said, okay? Not advanced beyond this course, but right now we are we will be studying this at depth very soon, but we are trying to take a shot here. Can we use our understanding so far to do this? Okay. So let us think this way. Where is the new mean position, the average position? What used to be earlier the x-axis, right? If you look at normal sine graph, that has now shifted up, right? The average position. And that happens, not typically, that always happens when you shift the entire graph vertically up. Okay. So the equation of this graph would be y equals something sine x, okay, plus 1, right? There is a vertical shift of 1 units. Then in terms of that something sine x, let us see if the angle itself has been changed. Okay, is it sine x or is it sine 2x, sine 3x, For that, we look at the period of the graph, right? And if you observe here, it makes one complete cycle in the length 2 pi, which is normal. That's what sine x original period is. So that tells us that the angle is still x. Okay, there is no modification there. But if you simply take just sine x plus 1, at the most its max value should have been only 1 plus 1, 2, right? But you noticed here the max value is 3. The height of the Q is at 3. That is because if you see from the average position, okay, the mean position is here at the height y equals 1, and the distance from there to Q from 1 to 3 is 2 units. So if you think of this in terms of stretching, the graph of sin x has been stretched 2 times, right? What was an original height of 1 has been now made into a height of 2. And that you might remember from college algebra or pre-calculus. is when you multiply the function at the front. Okay. Now, if you check carefully, this equation corresponds to that graph. And I will give one more, like, validation why this equation is correct. That is from the range. Okay, if you try to take this equation and write its range, range of this equation would be the max values of sine is -1 to 1, right? So 2 times -1 to 1, minimum and maximum, the range of sine, plus 1 you are doing. Now this is some kind of, like, arithmetic which you have to understand in the context. So that could go all the, now if you take a range of -1 to 1 and multiply by 2, you're stretching by 2 twice. That goes now from -2 to 2, right? And then you're adding 1 to the whole range. That is, you're shifting the graph up. So which will take you now from -1 to 2 plus 1, 3, right? Both lower value and upper value will go up by 1 units. -1 to 3. And if you check here, that's what exactly is happening in terms of range on the y-axis. It's from -1 to 3. Okay, so that equation makes sense for that graph, right? This is our attempt to try and understand the transformations of sine and cosine. Okay, take this. Let us repeat the same process. Write the coordinates of P, Q, R, and S, and then we will try to see, write an equation. Okay. Now in this case, the reference point given to you, to make some deductions is here, and its coordinates are 7 pi over 3 comma 0. So it seems this is still your x-axis, and that's your y-axis, and looks like, that's the average position here. So there is no vertical shift here, you can see, but there is a horizontal shift, right? Your graph, doesn't start at origin like the normal sin x graph. So the previous one was vertically shifted, this one is horizontally shifted. We will think in a second, how that plays into the equation. And then when it comes to the y coordinates, clear levels are not given here, so I'm going to go with the leveling now. I'll call each one of them as 1 unit. Okay, so say that is 1, 2, and 3. All right. And on the x-axis front, if the value here is 7 pi over 3, let us count if each of these small marks here is pi over 3. Okay. 1, 2, 3, 4, 5, 6, 7. Okay, so that seems to be correct. So, for example, P here corresponds to pi over 3, 2 pi over 3. Next will be pi. Next would be 4 pi over 3, 5 pi over 3. Then you will get 2 pi. And when you add, pi over 3 to 2 pi, you get 7 pi over 3. Okay, so that seems to be the division of like the scale on x-axis. Okay, so let's do some negative also here. -1, -2, -3. -3. Okay, let us write the coordinates. The coordinates of the point P x pi over 3 and y value is 0. Okay, it's on the x-axis. Q. Please, you go ahead and write, okay? And don't wait for me. You go ahead and write and check with me. Q is interesting. We need to do more calculation, okay? Because Q is halfway between these two, okay? Between pi and 2 pi over 3 and pi, it's halfway in between there, okay? So, how much would that be? If you do the calculation, I will do right below here. So it's 2 pi over 3 plus pi divided by 2. Okay, you need to do that calculation. Make that 3 pi over 3. So you can add, it will be 5 pi over 3, and the 2 and 3 will multiply in the denominator. You will get 5 pi over 6. Okay, in the middle. Actually, if you think in terms of degrees, you might be able to do it quicker. I will tell you that in a second. The y value is 3. Pi over 3 is 60 degree, remember. Okay. So here we are at 60 degree. I'm starting with P. Okay, 60 degree, 120 degree, and 180 degree. So Q is between 120 degree and 180 degree. That would be 150 degree. 150, right? That is 5 times 30 degree. 30 degrees pi over 6. That's how you are getting 5 pi over 6 if you want to do calculation that way. Okay. R is at 4 pi over 3 and 0. Finally, S. The story of S is similar. Okay. It is supposed to be, now the graph might look a little crooked, but it is supposed to be between 5 pi over 3 and 2 pi. I am going to do that with the degree logic. Okay. Pi over 3 is 60 degrees. So 5 pi over 3 is 300 degrees. 5 times 60, 300 degree. 300 and 2 pi is 360, of course. Between 300 and 360 is 330. 11 times 30. So that is your 11 pi over 6. And the y coordinate now is -3. Okay, those are the coordinates of point S. Okay, what about the equation? Think here, no vertical shift. So it will be something in, let's say if you just go with the sine x, you are not going to add anything. So it will be y equals, maybe we multiply something, we'll see that, sine and some angle. What do we multiply with? The word for that, I did not talk, I think use the word previously. The word is amplitude. Okay. The distance from mean position to the peak position is called amplitude. Okay. In the regular sine graph, sine x, the amplitude is 1. Okay. Here, the amplitude is 3. And that appears in the equation here. The graph has been stretched 3 times, right? 1 has become 3. So from our understanding of, the transformations of graph, we should multiply the output by 3. Sine x. Now there is no vertical shift, but there is a horizontal shift, right? And the horizontal shift is to the right. Right shift by how much? Pi over 3. Because your starting point P is there, right? What would be at origin is at P here, which is pi over 3 to the right. Again, if you remember from pre-cal or college algebra, that would be minus. When you shift to the right, you subtract minus pi over 3. So the equation of this graph is 3 times sine x minus pi over 3. Okay. I'll go back here and talk that here the amplitude is 2. Okay. That's why it was 2 sine x and vertically shifted plus 1. Here 3 sine horizontally shifted, so x minus pi over 3. Right? Now we can answer this question. Okay. How can we obtain a generalized sine or cosine function starting with the graph of sine x or cos x? And the answer is using transformations. Okay. Like what? Shifts, that could be, up or down or left or right, all these four possible shifts. Okay. Left shift, right shift, up shift, down shift. Or you could do stretching, which also includes shrinking. Okay, if you multiply by a factor less than 1, and you might sometimes do reflecting, reflections, and so on. Okay. um the all the this what we call linear transformations can be used to get the generalized graph as we just saw. Okay, now let's make that concept solid by looking at, in general, what do those transformations become in the equation. Like the two examples we wrote just now, you multiply that sign by some coefficient at the front, right? Then you change the x by adding or subtracting, and then you might add overall something to the function. What does each of them represent? The A represents the amplitude, which is the stretch factor. By how much factor have you stretched the graph? Vertical stretch factor, right? Okay. B, there is a name for it, which I have not used. It's called phase shift in the language of trigonometry, and it is your horizontal shift. In ordinary graphing, we call it horizontal shift. In trigonometry, we call it phase shift because it is related to the angle. We're shifting the starting value of the angle, and that is called phase. Okay, so phase shift is on x. And finally, the C is your vertical shift. I'm not sure if it has a special name. In our context of the mean position or average position, you can remember it as shift of the mean line or position. Okay, when the usual mean position for sin x is the x-axis when y equal to 0. If there is a vertical shift, that average value or the mean position, mean line can move up or down. Okay, given by C. Right. We will now do some practice problems using all of these ideas. Sketch the graphs and label 5 key points. There are 2 questions of this type we are going to practice here. You should learn the technique fully from the first that I will solve, and then apply that to the second one on your own and then check your work with me. Okay. Now, the best way to handle this kind of questions is you start with the original graph of sin x. Remember, we asked that question earlier. How can we start with a sin x and cos x and obtain a general graph, right? We actually follow that approach. So that means what we need to do is we need to identify the type of transformations that are being done here. Let us look into that first. The answer to that comes from the equation. The equation is y equals 3 times sine x minus pi over 6. So vertically, what have we done? And what does that do to amplitude? We stretched it by a factor of 3, and that makes the amplitude equal to 3. The amplitude of sine x is 1. 3 sine x will be 3. Okay. Did we change the period of the function? That depends on whether we horizontally stretched it or not. If we did anything horizontally, it would have appeared in the coefficient of x, which it has not. So we did not do any horizontal stretching. Period has not changed. Period of sine x is 2 pi. What does that minus pi over 6 do then? That is your horizontal shift. And if you are subtracting, that means you have shifted to the right. Okay. Right by how much? Pi over 6. Okay. And the range of the function will depend on the amplitude and any vertical shift. There is nothing added here. Okay. That part is missing. So no vertical shift. Only the amplitude has been multiplied by 3. So instead of -1 to 1, the range is now -3 to 3. Okay. So these answers, and in this process, we are now very clear the kind of transformations that have taken place. Simple, only two actually, if you think about it now. Your graph of sine x was shifted to the right by pi over 6 units, and then it was stretched vertically by 3 times. Or in the other way round, doesn't matter. The order of these two operations does not matter. That is something you also want to think and be clear about. Okay. So you don't have to worry, do I need to do that in a particular order? Here you can see it doesn't matter. Okay. So what is the approach then to graphing? We want to sketch the graph and label 5 key points, right? So what you can do is you start with the graph of sine x, sketch it, and then apply these operations to 5 key points on that graph. That is the reason we had looked at 5 key points in the graph of sine and cosine earlier. Okay. You might also want to do this as a table separately. Okay, you can draw a table like this in which you make a list of points, the images and the original points and what they become after the transformation. Maybe something like this here. Okay. I might write and erase here because we have limited space. If you are taking a note, and if you're writing with smaller fonts than mine, you might be able to fit everything in. Okay. So let me take some points here. Okay. I will write here sine x and 3 sine our function here x minus pi over 6. Okay. We will look at these two functions. On sine x, okay, now coming to the graph, which cycle of sine x you want to consider, right? You can just go with your usual graph from 0 to 2 pi. Okay, we have done that before. So this time, just for the sake of developing more understanding, I will take another cycle, not the fundamental period, not the fundamental cycle, something else. As long as you take a length of 2 pi, it's one cycle of sine x, right? So why not we do it from minus pi to pi? Okay, maybe a little bit more to the right to be accurate. So let us take this period, minus pi to pi, and uh, at this point, you should be comfortable. The graph of sine x from minus pi to pi would be something like this. Okay, and the low will come at minus pi over 2. The high will come at pi over 2, and the 3 points on the x-axis will be at minus pi, 0, and pi, right? And now we know what those coordinates are. I will not write on the graph, that will be cluttered. I will write those coordinates on the table on the left side. Okay. Say I begin with the leftmost point. Its coordinates are minus pi, 0. Okay. What I want to get is the new point on the new graph corresponding to this minus pi, 0. So effectively what you should think is whatever actions we do on the graph is done on each point of the graph, right? So if I take this point minus pi comma 0, I stretch it by a factor of 3. That does not change the 0 vertically. It is a vertical stretching. So that remains the same, step 1. Now I'm going to show that flowchart here. Okay, that is why I said, you might want to do a lot more work on a separate paper if you want. So this will be a two-step process, okay? In the first step, when you do stretching, nothing happens. Vertical stretching, nothing happens, okay? But then you are shifting that point by pi over 6 to the right. It is important to understand it's a right shift, okay? And when there is a minus sign in the equation, that is a right shift. Some of you might, be a little hazy on your college algebra or pre-calculus, so I'm repeating stuff here, okay? That means now this is right shift here, and when you do that right shift, minus pi plus pi over 6, you will be at minus 5 pi over 6. Do the calculation, okay? Minus pi plus pi over 6 will be minus 5 pi over 6. So with that, like that flow chart, your original point minus pi 0 becomes minus 5 pi over 6 0 in the new graph. And where's that? That minus 5 pi over 6 would be 1/3 of the way between minus pi over 2 and minus pi. Pi over 6 is 30 degree. Okay, if you are wondering, what is the logic here. Pi over 2 is 90 degree, pi is 180 degree. That gap is 90 degree. So pi over 6, 30 degree. So 30, 30, 30. No? 120 minus 90 minus 120 minus 150, which is 5 pi over 6. So your image point is here. I'm going to make a big blob and then mark it. That's the point. Okay. And I will write that here, minus 5 pi over 6, 0. Now you do this process, this table, for 5 points, all the 5 points on the original graph. Okay. And what you can do is you can keep the rest of the data same, sorry, the flowchart the same, just change the points here. And maybe I will also use a different color, so it will be clear. Now the next point you can take on the graph is at minus pi over 2. which is here. Let me just quickly write, I will erase it again. At minus pi over 2, the value is minus 1. Okay, that's my point. And so that's here, minus pi over 2 minus 1 in the original graph. Find its image in the new graph. So here, minus pi over 2 minus 1, you stretch by how many times? 3 times. Okay, the stretch factor is 3. And when you do that, this will be minus pi over 2 minus 3. Right? Now that's not on the x-axis, that's away from. So there is some y, there's some height there or depth. And so when you stretch, it will move to negative 3. And now you do the right shift. So from minus pi over 2, further pi over 6 to the right. Okay. Pi over 2 plus pi over 6 will be 3 pi over 6 plus pi over 6. I'm trying to do the calculation here. Okay. 3 pi over minus 3 pi over 6 plus pi over 6. That's minus 2 pi over 3. Again, please do your own calculation. Okay. Minus pi over 2 plus pi over 6 will be minus pi over 3. And the vertical height is minus 3. Okay. And that point you can now make it on the table here. And then go to the next point. And you can also mark it here in the graph, by the way. In the graph, your minus pi over 3 is here. Okay, the second one from the origin, pi over 6, and 2 pi over 6 is pi over 3, the second. And the y value is minus 3. I'm just assuming the scale. Suppose this is at minus 3 here. So that will be your point. Okay. And then next point on your original graph is at 0. 0. What happens to that? We will speed up a little bit now. Okay. I hope you are comfortable understanding the logic. Take the point 0, 0, because it becomes routine, you can speed up. Take the point 0, 0 on the graph. I will show it and then I will remove it. Okay. I circled there in the center. That one. That's the point 0, 0. Stretch it by a factor of 3. Nothing happens. It will still be 0, 0. And then you shift it to the right by pi over 6. Okay. That will be pi over 6, 0. So that's here. Similarly, my next point is here, which is at pi over 2, 1. Okay. Let us go ahead and apply transformations in that. Okay. And that will be pi over 2, 1, stretched by a factor of 3, and then move pi over 6 to the right. So pi over 2 plus pi over 6. Pi over 2 is 3 pi over 6 plus pi over 6. So 4 pi over 6, which is 2 pi over 3. Okay. And where's 2 pi over 3 in the graph? 2 pi over 3 is 120 degrees. So it's the first one here. The first red after pi over 2. 2 pi over 3 is 120 degrees. That's how I figured that out. Okay. And the y value is 3. So say here. Okay. And I can put that on my table here. Pi over 3, 3. And finally, the last point on the right side is at pi comma 0, right? The point I will show briefly and remove it here at pi 0. Okay, that point, how does it grow graphically? Okay, that will be pi 0. When you stretch, nothing happens to the y coordinate. Then you add pi over 6 to the right. Clearly, that will be 7 pi over 6, 0. And that's your image, 7 pi over 6, 0. Here, after pi, add pi over 6 to it. You are there. I'll probably show it like that. Okay. I think we didn't level one of the points. That was, we missed it. I'm going to show now. It was here. Pi over 6, 0. Okay. So now you focus on the red dots. Those are your 5 key points on that graph. Okay. And try to sketch now a graph of sine x following these key points. I will make an attempt here to be as smooth as possible, like that. And I'm going to adjust that down. Okay, that would be the graph of, this is 3 here. Okay, so this will be the graph of 3 sine x minus pi over 6. Lot of, okay, but very interesting exercise. I'll zoom out and show the whole thing. If you need, take a breath, have a relook at it and try to understand everything. Replay the video if you need, follow all the logics that we did, and then go ahead and do this. Do it yourself and then check my explanation next. I will repeat the whole thing that I did with that graph here also, but you do it first. Okay, so the equation is negative 2 cos x plus pi over 3 minus 1. So now instead of 2, there are 3, actually 4 if you want to divide further, actions that are taking place here. Number 1, you would have noticed you are multiplied by a factor of 2. So your amplitude has become 2 now. Phase shift, you are adding plus pi over 3 in the equation. That is a left shift. So your graph actually shifts left by pi over 3 units. Okay. And what happens to the range? I'll write on the top here and then write the final answer down. Okay. As far as the range is concerned, cos has the range minus 1 to 1. Right? When you multiply by 2, that range will be minus 2 to 2. What if you multiply by minus 2? Doesn't matter. It's the same range. Okay. That range is the values, When you multiply by minus 2, the graph will flip. But the lowest and the highest points are the same, Where you had 2 earlier would be minus 2, and where it was minus 2 will become 2. But the range remains the same. The width, vertical width remains the same. And then you are subtracting 1. So you are moving the whole graph down. That will bring that down to negative 3. And the highest point will come down to 1. From 2 it will come to 1. Okay. So the range of this function is -3 to 1. All of that helps you sketch the graph correctly, accurately. Okay. Now, in terms of transformations, let's make a list of that actually. Transformations. What else? What all things have been done to this poor graph? Okay. Uh, the transformations, again, I don't think there is a strict order here. Some of them might be interchangeable. You can do them in any order. Let me see. Okay. Number one, the graph of cos x. Okay. Let's say I shifted right first. No, left, sorry. Left shift I did first on that pi over 3 units. And then I stretched it vertically. Vertical stretch 2 units. Factor, okay, factor of 2. And then the minus sign is reflection on x-axis. Think about it, okay? If you are at a, like, let's say, -2, like y coordinate, if you take the negative of the function, the value will become positive too, right? So the effect is reflecting on the x-axis. So the next action we did is the reflection on x-axis. And then finally, you subtracted 1 from everything, right? So downward shift, I can write like that. Downward shift 1 unit. Okay, those are the transformations on the graph of cos x. All right. So this time, let us do the transformation on the original graph. Now, sorry, the fundamental period. In case you did a transformation on, let's say, from minus pi to pi, that's okay. Okay. And you can follow what I am done here. Your graph and my graph would be the same, except, horizontally they would be in a different shift. Okay. But you'll understand if you have done it whichever way. I will start with my, let's say, 1 here, but the factor 2, right? So maybe I can take a little bit bigger value. 1 here, 2 here, that will be the max value. -1 here, so -2 here will be my mean value. And I want to divide, let's say here is my 2 pi. This is anyway 0. So I can zoom in, I guess. And so pi can be in the middle here. So your pi over 2 can be the middle of that. 3 pi over 2 can be here. Okay. And your graph of cosine, let me do that dotted, would be at 0 it is 1, at pi over 2 it is 0, at pi, oh no, not that low, at pi it goes to -1, 3 pi over 2 back to 0, and at 2 pi back to 1, right? That's the graph of cos x, the fundamental period. What are the transformations? What are the new points? The new points, say you take the point 0, okay, I need to change that. Say you take the point 0, 1. Okay, that 0, 1 will become, after all of this, let me talk about it, do the mental calculation and write the final point if possible, we'll see. Okay. Left shift pi over 3. So that will be at minus pi over 3 comma 1. Then stretch vertically by 2. So that 1 will become 2. You reflect. So it will become minus 2 and 1 unit down. So I am seeing minus pi over 3 minus 2 minus 1 minus. I know I did mental work here. I will repeat. Okay. I will go through this sequence of those 4 transformations that I have written on the left. Okay. 0 comma 1 left shift will make it pi minus pi over 3 comma 1. Particle stretch by 2 will make it minus pi over 3 comma 2. Reflection on x-axis will make it minus pi over 3 comma minus 2. 2 will become minus 2. And then you downward shift 1 unit. So minus pi over 3 minus 3. Flow. Okay. So, oh, thank God. I think I should have been a little careful. Luckily, I didn't take a very big scale. So minus 3 is somewhere here. Okay. Now you assume that you extend your y-axis down, negative y-axis. Okay. And minus 3 is here. And that's happening at what? Minus pi over 3. Now, according to our scale, pi over 2 is almost there. So pi over 3 would be almost here. Okay. Not there actually, a little more, somewhere here. So down here, that would be your point. Okay. Which one? I'm doing in purple color here. This one. Okay. That point 0, 1, its counterpart is the red blob down here. Negative pi over 3, negative 3. Repeat that for 5 other key points on the graph. You know what they are. 4 other now. 4 more. Second, third, fourth, fifth. Okay. Instead of taking your time in the video, what I will do is I'll make that list down here and you check it. Okay. That is the table I have created. You can check your points now. The 5 key points in blue color and their final new points, their images in the red color. And I have plotted approximately those red points on the graph there. I didn't label every single marking. Okay. Maybe I can just use a pointer and tell you. Okay. So for example, here, that is your pi over 6. So the point here is pi over 6 minus 1. And over here, pi over 2 is 90 degree here. After that comes 120 degree, which is 2 pi over 3. So that point here is 2 pi over 3 comma 1, which was the image here of pi minus 1. Okay, was 2 pi over 3 100. That point is here. And the next point, the next image point is 7 pi over 6 minus 1, which 7 pi over 6, right? So from pi, you add pi over 6, 30 degree. So that is 210 degree here. 7 pi over 6. So that brings you down here, 7 pi over 6 minus 1. And finally, down at the bottom footnote here, we'll see the point 2 pi comma 1 becomes 5 pi over 3 minus 3, right? 5 pi over 3 is 300 degree. Okay, that's somewhere here. And from there, 300 degree. Okay, now I'm thinking maybe a little bit more to the left. But anyway, from there to negative 3. Yeah. Okay. Now you have these 5 red points and you need to join them to make a cosine wave. I will erase my original graph now. Okay, otherwise it will be difficult to see. remove all of that, remove this, and maybe just that. Okay, now let us sketch. It will be the freehand graph. See, cosine shape, right? It has to have that cosine shape. And bent like that. And down here like that. Okay, not exactly, not too much bent like that, but more or less you get the idea. Okay, once now, write an equation of that form for this graph. With all the experience, we can do it faster now. Okay. So what's the new peak? The new peak is at pi. Let's look at one complete cycle. Starts here, ends here. Right? So what is shown here is more than a cycle. Okay, you have to understand that. One cycle is here of that graph. So if that is pi, this is halfway. This is at pi over 2. And pi over 2, pi, 3 pi over 2, 2 pi. So next one would be plus pi over 2, which will take you to 5 pi over 2. Okay, so from pi over 2 to 5 pi over 2 is your complete cycle. One cycle of the graph. And you can, if you start it at origin, that graph would have been sine x. So you can write this as a transformation of sine. We can go with this. All right. And let us do the scales on the y-axis. If this is 1 and that is 2, then you can see that the amplitude is 2. Okay. So your equation will be 2 sine, and it's in the same direction like original sine x, so it's not negative 2. If it is negative 2, this part would have been below the x-axis. Okay, you understand that? So it is 2, not negative 2. 2 sine, you can see that, instead of starting at 0, we started at pi over 2 to the right. So that in your equation is minus pi over 2. And the period, one cycle is still of length 2 pi, from pi over 2 to 5 pi over 2. The difference, the period is still 2 pi, so no change. You are not multiplying x, only shifting. And vertically, there is no shift because your mean position is still the x-axis. So that is your equation. Okay. Try here. So the shape here is that of the cosine function. Okay. The usual cos x would have started here, at 0, but we have started at pi over 2. So you can see the left shift, and looks like the scale is also the same like before. We call that 1 and 2. So you have stretched by a factor of 2, shifted right by pi over 2, and not done any reflection. It's in the same direction. So your equation will be y equals 2 cosine x minus pi over 2. Okay. You can, process faster once you get more clarity. Okay. So these two questions are, about concepts, making our concepts sharper. The dash of a sine wave is the absolute value of the half the difference between the maximum and minimum y coordinates on the wave. What's that? That's another way to define that term. Maximum and minimum y coordinate, take that distance and half of it. What does that represent? I'm sure you got it. That's amplitude. Okay, another way to define the amplitude. I had defined it as the distance from the mean position to the peak, right? But it's the same thing from the mean to the lowest value. So if you look at the highest and lowest, half of that is the amplitude. That's what this definition says. And the concept of odd and even function here. You remember this again from your earlier studies. Even function is like the even powers, like x square, on the negative and positive, they give the same output. Odd function is like the odd powers. When you input the negative x, your output also changes the sign. Now, based on that, you decide whether sine x and cos x are odd function or even functions, and give your reasoning. Why do you think? Why do you choose that answer? There could be different approaches to this. I will fall back to the most basic reasoning, that is the definition. Okay. Now, how are sine x and cos x defined? The unit circle definition is based on their coordinates, right? Now let us look at sine x. Okay. Sine x, or I will use theta because x will be confused with x coordinate here. Let's go with theta for the angle. At any angle theta, the sine, or okay, we can go with x. At any angle, theta, the sine is the y coordinate, right? So when you are at a positive angle here, um, okay, you can go with the angle here because the angle is not exactly here. We can be plotting the angle here. Okay, so the angle theta is plotted here, and let's say the angle theta is represented by x here, the variable angle, okay, on the x-axis. So at any angle x, the value of the y coordinate is sine x, right? And if you go to a negative angle, okay, if you try to evaluate sine of negative x, the negative angle is in the concept of angles, when you measure a negative angle, you can think of it as moving clockwise. So you will go to fourth quadrant. If you go to fourth quadrant, your y coordinate will become negative y, right? The same amount if you move to the fourth quadrant from positive to negative, your plus y will become minus y. So your result, the value that you will get would be negative of what it was before. Okay, so sine x is odd. And what about cos x? Cos x is the x coordinate, right? Now for an angle, if you go from positive, I'm referring back to the same diagram. I'll erase it and write it again here so you can see it here. Okay. If I'm at an angle here, let's say theta, and if I go to negative theta, I'm moving to the fourth quadrant. The x coordinate does not change, right? And cosine is the x coordinate of that angle, which remains the same. So cosine of negative theta will be the same as cosine of theta. Hence, cos x is an even function. Okay, very interesting exercise. Think about that. With that, we are at the end of that section. I will see you for the general sine and cosine waves in the next video. Thank you.